Aha, good. Somebody showed up. I just had turned on the recorder. So Justin's here. Today's the 22nd. All right. All right. Just about was to launch into how nobody was here, blah, 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 but now you came in. Save the day for everybody. All right. Meanwhile, I'll turn on the projector now that somebody's in the room to see it. And I'll turn on the light. If you wish. Okay. Okay, first thing I was going to do is ask if there are any questions for anything we've done so far. Okay. All right. Now, do you have some sort of remembrance of where we were last time? I have one mark at the bottom of page 9 on the discovery down there. I don't know if I said we would do that or not. I had my page in here at the beginning of 1.2. Did we finish 1.1? Do you remember? Huh? What's the last you had? Example 8 or example 9? Huh? Which one? What's that? Did we finish it? Or is that where we're starting today? Okay. Well, then I didn't make a mark at all. Okay. Okay, but we did do 8. I sort of remembered that because we talked about it. Okay, so example 9. Here's the system of equations. I'll get my pen set up. Okay. X sub 2 minus x sub 3 is equal to 0. X sub 1 minus 3x sub 3 is equal to negative 1. And minus x sub 1 plus 3x sub 2 is equal to 1. Okay. Now, so we didn't do this. You don't have this in your notes. Okay. I've done this so many times. It seems like it was just yesterday I did it, but maybe it was one similar to this. Okay. Now, it seemed like to me that someone said, but you could just say x2 equal x3. Yes. Hey.
I was trying to help the Math 186 teacher.
What's that?
The Math 186 teacher.
Yeah, what about
Because we don't have a room.
You don't?
Can I put her in 201? It doesn't look like there's anybody in there for her time slot.
Okay.
Is that okay?
Yeah, and yeah, that's what I recommended in the email I sent.
Well, Dr. Marable wanted me to just follow up with you before I made the change.
Right.
She wanted me to talk to you personally.
Yeah, because I recommended that, but I didn't know if you had availability then.
We don't use 201 anymore. It's not our room.
Oh, you don't?
No.
Who does
we
it
don't
belong
have
to?
access to it.
Really?
No.
Who does it belong to? Us?
It's biology and math and English and whoever.
Right. Okay.
We can't use it anymore.
Okay. Wow, I didn't know that.
We only have 2 rooms. 106 and 170, and that's it.
Wow.
For lecture.
Okay.
All righty. Well, thanks so much.
All righty. Yeah. Sorry about that. Okay. Because someone had suggested we could just set x2 equal x3 and then make this a 2 equate to, and that certainly would work. But because we're heading towards something else, what I wanted to do was, it's a little bit longer, but it is going to be what we're going to be doing in the future. What's the first thing we wanted? The first coefficient to be 1. Well, you don't there, in the top equation, it says 0. This one is a 1. So what I suggest is you flip these two. And remember, that's one of the operations that's allowed. Exchange any 2 equations. So my next thing would be to write this as x of 1 minus 3x sub 3 is equal to minus 1. X sub 2 minus x sub 3 is equal to 0. And minus x sub 1 plus 3x sub 2 is equal to 1. Okay? Now we got what we want. We want the leading coefficient of the first thing up here to be a 1. Now what do we want after that? A 0 below it. We got that just by flipping it. And then we want a 0 below that as well. So what would we do to get this to be a 0? Add those two together. So equation 1 plus equation 3. Equation 1 plus equation 3 will be the new equation 3. So that would then be, leave 1 alone, x of 1 minus 3x sub 3 is equal to minus 1. Leave number 2 alone, x sub 2 minus x sub 3 is equal to 0. And then, what will your new equation 3 be when you add 1 and 3 together? What do you get first? Say again? 0. Okay, that's good. And then you add this and that, and you get 3x sub 2. And then you add this and that, and you get minus 3x is 3 plus 0, right? Okay, you get minus 3x sub 3, and that's equal to, add those two together and you get 0, right? All right. So quick review. We got a 1 as a coefficient here, just like 1, 0 below it. Then we go to the second equation. We want that first coefficient to be a 1. We got it. So to get that to become 0, what would we do? The next thing we want is this to be a 0. How do we get that to be? Minus 3 times this plus that will make this 0, right? Okay. So minus 3, equation 2. Add it to equation 3. All right. So equation 1 stays the same. X of 1 minus 3x sub 3 is equal to minus 1. Okay. Equation 2 we leave alone. X sub 2 minus x sub 3 is equal to 0. Okay. And then the third one, what does it become now? Minus 3 times this. Make it minus 3x2 plus 3x2 is minus 3x2 plus 3x2 becomes 0, okay? And then a minus will be plus 3x3. Minus 3x3 becomes 0. So this side becomes 0, and the other side, okay, sorry about that. The other side, minus 3 times 0 plus 0 is 0. All right. Now this time, you get, at the end, something that's always true. If you remember example 8, if you look at that, we wound up with something like 0 equal negative 2. Never true, so therefore there's no solution. This one we get something that's always true. 0 equals 0, 7 equals 7, minus pi halves equal minus pi halves. Whatever it is, it's always true. That means you have an infinite number of solutions. Okay? Now, how this is going to pan out just about every time, you're going to have everything being 0 at the bottom. And that's exactly what we got this time. And 0 is always equal to 0, so therefore, that is an infinite number of solutions. Now, to get what the solutions are, we go back and do what we were talking about before. You have a leading coefficient of 1 here, you have 1 here. We don't have any for x of 3's. So therefore, we let that be our parameter. And we say let x of 3 equal 0. Not 0, equal t. Or whatever other parameter you want to name it. I don't care. Their favorite is t. Then this one says x of 2 minus t is equal to 0, which implies that x of 2 is equal to t also, right? And then you go back to the first one, you say x of 1 minus 3 times x of 3, which is t, minus 3t is equal to minus 1, and that implies that x of 1 is equal to 3t minus 1, when you subtract 3t from both sides. So now your ordered triplet is 3t minus 1, t, t. Those are your solutions. Why the t didn't show up, I don't know. Okay. I don't know. That's great. Okay. 3t minus 1, t, t. So pick a t, any t. T equals 0. That would be minus 1, 0, 0. 0, 0, that works there. Minus 1, 0, that's minus 1. Minus 1, minus 1 is 1, plus 0 is 1. Yes, so that works. Oh, 10 o'clock scholar. Terrell is here. All right. All right. So, any other t you wanted to choose? 7/45 over 5, or anything like that you want to put in there. Put it in for t, put it in for t, put it in for t. You got an ordered triplet. That is guaranteed to work. Infinite number of solutions. Any t you chose to put in there, you'll get an answer. Okay. And that's exactly what they got as well. Now, any questions on that? This is on page 9. That was example 9. There is a little discovery at the bottom of the page, and sometimes they take longer than they're worth. This one I don't think is going to be so awfully long. I'm not going to do what it says. It says graph the two lines represented by a system of equations, and then use Gaussian elimination to solve the system, and then compare the graphs. Well, rather than doing that, let's just use Gaussian elimination. So here we have x minus 2y is equal to 1, minus 2x plus 3y is equal to negative 3. Okay, now, if you did want to graph those two, I'm not going to graph them for you, but I'm going to talk through them. How I would do it was I'd add 2y to both sides and subtract 1 from both sides. So you have 2y is equal to x minus 1, divide by 2, and you have y is equal to 1/2 x minus 1/2. Well, that would be a line that the y-intercept is minus 1/2, and it would go like this. Slope of 1, so it goes to here. So that, slope of 1/2. So up 1 for every 2 over. So that would be through here, through there, through there. So it would be a slope of 1/2. Okay? If you did the same thing for this one, that would be 3y is equal to 2x minus 3. Divide by 3, you get y is equal to negative, to 2/3 x minus 1. That has a y-intercept of minus 1, and then it's going up 2 for every 3 it goes over. So it goes along like that. Okay? Now, those are two lines that are really close to each other and not quite parallel, but not a huge difference in slope. This has a slope of 1/2, this has a slope of 2/3. So they're really, really close. I wouldn't graph them. But let's do Gaussian elimination. What's the first thing you want for Gaussian elimination? The coefficient of 1. You got it. Okay? So you're happy there. What do you want underneath that? 0. How do you get that?
Can you subtract?
Second?
Can you add?
2, yeah, multiply 2 times the first, 2 times equation 1 and add it to equation 2. Right? That should do it for you. So that would produce, leave the first equation alone, 2 minus x minus 2y is equal to 1. And then when you do that, what do you get? 2 times equation 1, 2 times x is 2x minus 2x is 2x minus 2x is 0. Okay, that's exactly what you wanted. And then 2 times minus 2y would be 2 times minus 2y is minus 4y plus 3y would be minus 4y plus 3y. Minus y, okay? And that would equal, and then 2 times 1 is 2, minus 3 would be minus 1, okay? And then what you want down there is that coefficient of y to be 1. It's a minus 1, so what could you do to make it a 1? Second? Don't add. To get the coefficient of y to be 1. It's a minus 1 now. Either multiply by minus 1, and that'll give it to you, right? And here's how you do it practically. Okay, notice the sound effects? You just multiply by, okay. So y is equal to 1. Okay. Now, what you have then is that same graph that you had before that was something like this, and now you have y is equal to 1 here. They are going to intersect at the same place. Okay? And I don't know why they had you graph it, but that's what they had you doing. And y is equal to 1. Well, what is the x value where y is equal to 1? Well, if y is equal to 1, you can plug that in either one of these equations or back substitute, and that would be x minus 2 times 1 is minus 2 is equal to 1, and that would be x is equal to 3. Okay? And sure enough, that's what they got. Then x equals 3 is like this, and y is equal to 1 is like that. So you have the same 2 points of intersection, you just are wiggling them around until you have one vertical and one horizontal. So I'm not sure that was very enlightening. Anyway, that does finish 1.1. So homework exercises, I've given most of these before. Do any of the odds 1 through 5. They're all at calcchat.com. Do it either 7 or 9. They're both at calcchat.com. Do any of the odds 11 through 23. They're all at calcchat.com. Do any of the odds 25 through 29. They're all at calcchat.com. Then do any of the odds 31 to 35. They're at calcchat.com. Then do any of the odds 37 through 55. There's a whole bunch of them there. Just do enough of those that you feel confident you know what you're doing. And here's Jordan. Good deal. Okay, we just finished 1.1, and I'm giving homework exercises in it. Then do either 57 or 59. They're both at calcchat.com. Then do either 61 or 63. They're both at calcchat.com. Try doing 65. That's an applied problem. 67 is a true-false. Now, you're not going to have many like that on your test, but it's still good to think through. Then you can do 69 if you like. Try to do either 71 or 73. They're both at calcchat.com. 75's at calcchat.com. Do any of the odds 77 to 81. They should all be at calcchat. And do 83. And then 85 is a writing problem. Think through that anyway. 87, I think, is one you could do. And 89 is certainly one you can do. 91 is one you could do. So, all those odds are at CalcChat. All right. Any questions? 1.1. Let's move on to 1.2. And here's Peyton. Wondering, anyone having trouble getting here on the expressway? No, okay. The malfunction junction downtown Birmingham is really malfunction now. It's completely being torn apart anyway. Or actually, a lot of the bridges leading to it and in it are being taken down, and they're putting in the new. I had to find an alternate route this morning, and since I tried to go across UAB, I found out I'm not going to try that again, okay? I used to do that on Fridays, but Fridays UAB must not be as busy as Monday through Thursday, or lots of people off the interstate were coming through UAB, which either one of those produced a really ridiculous situation this morning. So I'm going to try Plan B tomorrow and see if it works any better. All right. So we just finished 1.1. We're getting ready to start 1.2. And the title of this are Gaussian elimination. We've heard that before. And Gauss-Jordan elimination. Oh, we add another guy to it. Okay? But before we do that, we're going to introduce the concept of a matrix. And hopefully what we've been doing is leading us right to this point, so this is not going to be a big stretch here. Okay? Now, Section 1.1 introduced Gaussian elimination as a procedure for solving a system of linear equations. What we're going to do now is write those equations without any variables. But we're going to be very careful where we put everything, because that's the placement is going, we have to remember those represent our variables. So if you leave all the variables out, all you got left are numbers, okay, which are entries in what we call a matrix. So here's what a generic M by N matrix looks like. M and N are both positive integers, not fractions, not decimals, not negative, positive integers, not zero, okay, positive integers. Now, each letter here has two subscripts. We'll talk about that in a minute. Subscripts are just indicating position. The letter represents a number. So the first one's going to be A11. The next one's going to be A12. The next one's going to be A13. And we're going to keep on going like that, dot, 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 until we get to A1, N, I believe it is. Yes, N. That represents an array of numbers, is one thing. It could also possibly, potentially, represent an equation with no variables in it, just the coefficients and possibly the constant. That's what we're going to let it be at first. The next is going to be A21, A22. You tell me what you think next is going to be. 2, 3, dot, 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 A2N. Perfect. What you reckon goes down here? A31, A32, A33, dot, 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 A3N. Okay? Let's just keep going dot, dot, dot down here. The last one is going to start off A sub M1, guess what the next one will be? M2, next one, M3, and then a dot, 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 a dot, 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 everywhere a dot, dot. Whoops. And what do you reckon the last one's going to be? MN, perfect. Okay? And now you get an idea of what we're talking about, the M's and N. When we say an M by N, that means we have M rows or equations and N columns. And those could be your variables and your constants if you had that. It doesn't have to be. It could just be any old array of numbers. It's a rectangular array, meaning there's nothing missing. They're not getting thinner or thicker or anything else. They have the same number of rows and columns. Every row has n entries, and you have m rows. Every column has m entries, and you have n columns. So m, the first is the row number, the second is the column number. Okay? And again, they may represent coefficients, or they could represent just about anything. We'll start using them as coefficients. Okay, that's called the matrix. And each entry, and by the way, for shorthand, we call each entry A sub ij, where I is anything from 1 less than or equal to I less than or equal to m, and j negative 1 is less than or equal to j is less than or equal to n. So the I stands for which row you're talking about, and the j stands for which column. Okay, and they'll all be between 1 and m for the rows and 1 and n for the columns. Okay, so we call that individual entry the ij entry. Okay. Now, again, the first entry is the row subscript. The second is the column subscript. The A is a number, any number. The M and the N are integers, positive integers, designating the first one designates row number, and the second designates column number. Okay. And Mama is here. All right. So we're just missing Vince and Daniel. All right. Now, if M was equal to N, and by the way, this is called, let me go back and say this, an M by N matrix. M by N. M being number of rows, N being number of columns. Okay. Again, this could represent equations, but it could represent just about anything. Okay. Now, here's a special one. What if M is equal to N? I called this a rectangular array because M didn't have to be the same number as N. M may be a larger number, N a smaller number. M may be the smaller number, and N a larger number. Okay? I said that backwards. M a smaller number, N's a larger number, M's a larger number, and N's a smaller number. Okay. My arms are waving differently. People at home couldn't see it anyway. Okay. So, what happens if M is equal to N? What becomes special about that? It becomes a square matrix, not a rectangular, but rectangle. Squares are rectangles too. They just have the same dimension. Okay? So if M is equal to N, we call that a square matrix. Now with a square matrix, then we have, if M is equal to N, then this would be a 1M, 1M, 2M, 3M, and this would be MM. That means you could go right down the diagonal here, and you have and you call this the main diagonal. From upper left to lower right, and you have exactly one main diagonal. Okay? So We don't talk about diagonals in rectangular matrices, but we do in square matrices. There is another diagonal like this, but that's not usually very important. I can't think of any time we ever use that. But the main diagonal is the one from upper left to lower right. For a square matrix, you have them. Okay. And those entries in that main diagonal are quite often important. All right, let's go to example 1. Some of these almost seem trivial and surprising. If you had a matrix that was a 1 by 1 matrix, what would you call that? Just a number, yeah. For instance, if that one and only one entry it had was 2, there's the matrix. It is a square matrix, technically 1 row, 1 column. It just has 1 entry, okay? They just happen to pick 2, okay? Now, if they have a matrix, they said B is a 2 by 2 matrix, okay? You could have anything as the entries. They just happen to pick a rather bizarre one, and this is the 0 matrix, 0, 0, 0, 0. Not a very interesting matrix at all. Daniel's here, so now we're just missing Vince. Hopefully he'll get here so we can have perfect attendance again today. I don't know why they chose to put them all zeros. It's, again, a not very interesting matrix for most of the things we're going to be doing, but it is indeed a true matrix. Now, here's C, and this one, they says, is a 2 by 3 matrix, okay? Now, it's only going to have 2 rows, but it's going to have 3 columns. So that's how I will indicate a 2 by 3 matrix quite often. But the one they did, they really make it bizarre, because these entries can be any real numbers. They can be positive or negative or mixed. They can be rational or irrational or mixed. They can be, they don't put any imaginary numbers in them. So here is their entry, a 2 by 3. E is the 1, 1 entry. 2 is the 1, 2 entry, and -7 is the 1, 3 entry. Pi is the 2, 1 entry. Root 2 is the 2, 1 entry. And 4 is the 2, root 2 is the 2, 2 entry, and 4 is the 2, 3 entry. Okay? You can put any numbers there you want, any real numbers. Irrational, rational. Positive, negative, fractions, decimals, doesn't matter, okay? So they picked a really outlandish one. But that's just an example of a 2 by 3 matrix. Now, as we were just doing, one of the first, and this will be a common use of matrices, is to represent a system of equations, okay? The coefficient matrix will be just the matrix made up of those coefficients, and then we'll augment that with a column matrix, which is sometimes called a column vector, and that will represent the equal to on the other side. Okay? So, I'm going to erase these. Any questions on this? All right. This is all pretty simple, nomenclature. Oh, man, I'm stiff and sore. I don't know why. I guess I've been sitting here too. I think it's because it's cold in this room and I've been sitting tensed up. All right. Here's a system of equations, going back to what we did in 1-1. X minus 4y plus 3z is equal to 5. Minus x plus 3y plus 3y minus z is equal to -3. 2x minus 4z is equal to 6. Okay. Now, what we're going to write next is what we call an augmented matrix. Okay? And why they do them in this order, I don't know. And then they're going to do the coefficient matrix. It would make a lot more sense to me if we did the coefficient matrix first and then do the augmented matrix. So I think I'm going to do it that way. Let's first do the coefficient matrix. What size will the coefficient matrix be?
4 by 3.
Okay, that's the augmented matrix. Okay, just the coefficient matrix would be 3 by 3. And in this matrix, we don't put any letters, we just put the numbers. So what numbers do we put there? 1, -4, 3, -1, 3, -1, and 2, 0, -4. That we call the coefficient matrix. Okay? Now, they're leaving it off, but what you could call the column vector or the column matrix of the constants, you could put like that. And then the augmented matrix would be what Peyton was calling the 3 by 4. That would be take the coefficient matrix and append to it the column vector or column matrix that are the constants. So that'd be 1, -4, 3, 5, -3, no, -1, I can't read my own writing here. -1, 3, -1, -3, 2, 0, -4, whoops, I keep wanting to put that, 6. Okay. Take out the equal sign. Okay. Now, that's the augmented matrix with the column vector, column matrix, whichever you want to call it, of the constants appended or augmented at the end of the coefficient matrix. Now, back when I first was learning linear algebra, we quite often put a dashed line between this, indicating the coefficient matrix and the augmented part. And that, to me, represented the equal sign. But notice what you've got to do here. Since you've taken out the variables, you have to be very careful that you keep the order in place. The columns are the coefficients of the various variables. This is the x column, the y column, the z column. If you wrote this some other way, you know, like 2x minus 4y is equal to 6 down here, then you're probably going to write your matrix wrong, okay? So it's a good idea to keep in your equations letters over letters and equal signs over equal signs, okay, to make sure that you're doing them right. And when you have a blank here, you do put in a 0 there. You don't usually put in plus 0y here, but you do in the matrix. You have to do something to keep it to be a rectangular matrix. You can't be missing an element. You have to put, if there's no element there, put a 0. Okay. So, equation, coefficient matrix, augmented matrix. All right. Now, what we were calling equations, we're now calling rows. Right? Now, we didn't used to call these anything. We will now start calling them columns. But what we were using, where we used the term equation before, we're now going to call them rows. And those are the second row corresponds to the second equation, and so forth. The rows, columns, they represent the coefficients or the constants And the coefficients have to be kept in the same order with the coefficients. -3, -4, 3, 0 would be the coefficients of the y variable. The constants must be over that with the understood equal sign here being right before that last column. Okay. Now, when you have then a matrix, an augmented matrix that represents a system of equations. See, we just made things a little easier because you don't have to write down the variables anymore. But you have to remember what those columns stand for. First column stands for the coefficients of x variables, second for the coefficients of y, and third for the coefficients of z. Okay. Now, we're now going to start talking rather about the elementary operations you can use on equations, and we're now going to refer to them as row operations. And we're going to say these are the elementary row operations. Same as we had for equations before. Anyone remember what was allowed? You can flip any two equations, exchange any two equations, that produces the same equivalent matrix. So now we say you can exchange any two rows. This one, this one, this one, this one, this one, this one. But you have to do the whole row, not just the first element, the entire rows. Okay? And this one we wouldn't want to do that because we have a 1 there right where we want it. Okay? So we wouldn't want to exchange any rows here yet anyway. Okay. Now, second operation you can always do is multiply any row by a non-zero number. Okay? So you can multiply this row by a -2 if you wanted to. Be perfectly fine. If you don't want to, we want that to be a 1. That's perfectly fine. Now, the third operation we can do, and this is the one we will be doing, is add a multiple of one row to another row. And we're going to do that very first. We're going to add these two rows together. A multiple, 1 times this row, add it to that row. And that's going to eliminate that first element. Right? Same as we did for equations, we're going to do now for rows. So we're going to call these now, rather than equation operations, we're going to call them row operations. Okay? So, do y'all need me to write these down? Okay, we'll get there in a minute. Do I need to write them down just for future reference? Because not all of you have books. Okay, so let me write them down. Interchange. Okay. When we're talking about equations, we said interchange any two equations. When we talk about elementary row operations, EROs, elementary row operations, we'll say interchange any two rows. Before we called them equations, now we'll call them rows. Okay? The second one, we said multiply any equation by a non-zero constant. Don't ever multiply by 0. Multiply by any non-zero constant. Now we say multiply a row, any row, by a non-zero constant. Okay. Whereas before we said equations, now we just say rows. Okay? And the third one, for equations, we said add a multiple of one equation to another equation. Now it's add a multiple of any row to another row. Okay. That's what we've got. Those are our 3 elementary row operations. Okay? Now, interchange any two rows. What we used to call equations. Interchange any two equations. The order of the equations doesn't matter. The order of the rows doesn't matter. Okay? Now, For now, we're not going to interchange any two columns because the columns represent the coefficients of the variables, and when you start messing with those, you'll forget what variable is in which column. So we're not going to do that now. Later will be fine. Sometimes it is allowed to do so, but not when they're representing equations. When they're augmented matrices representing equations, don't do that. Okay. Now, if we were operating on these three, I'm not going to do it, but here's what I do. I leave this one alone because you have the one right where you want. Then the next step would be add these two together. That's adding a multiple, one, of one row, this top row, to another, I'm sorry, that's number 3. Add a multiple of the top row to the second row. And the multiple will be 1. And this will be 0, minus 1, 2, 2. Okay?
What's the word after non-zero?
What's that?
After non-zero?
Oh, right here. Constant. C-O-N-S-T-A-N-T. I just didn't call it out. Remember, we never multiply by 0. Okay? That just wipes out all the meaning. What I would do next is multiply the top row by negative 2 and add it to the third row. And then that will make this a 0. So do that all the way.
Well, you do that if you already added the first one to the second one.
Say this again.
If you already added the first one to the second one,
Yeah.
why would you go back and also add the first one to the second one?
Okay. That's a good question. And here's what we're doing. We did it before, okay, and it's perfectly fine. What you're doing, you're using this 1, and we call that a leading 1, to make zeros underneath. So that's why we will use this one to eliminate that one, this one to eliminate that. We want to use the same thing to eliminate. Now, it would be okay to multiply this row by 2 and add it to that one, but not after you had already done the first one. So you could do that first if you wanted to, but usually we'll use the leading 1 to eliminate the others. It's just easy to do it that way. Okay. Now, then you'd use multiply negative 2 by that, add it to that. You leave this row alone when you multiply, add to that, and that will give you 0, that will give you positive 4, that, you know, whatever you get there. Now, if you remember, when you added these two together, you've got a minus 1. Next thing you want here is that to be, you have a 0 here, you want that to be a 1. It was a minus 1. So now we're going to multiply a row by a non-zero constant, negative 1, to make that a plus 1. And then you change the signs of all those. Okay? So you do things like this. In fact, my very first step for this system would not have been what I just said. I looked at this row and said, look, those are all even numbers. I'm going to divide everything in this by 2. Make that 1, 0, negative 2, 3. Or multiply everything by 1/2. That's a non-zero number. 1, 0, negative 2, 3. And then everything's so much easier. So I would have done this one the very first thing just to make that a simple row. And then all the others are much easier to do. Okay. So those are the elementary row operations, the things you're allowed to do. Now, let's do example 2, but I'm not going to quite do it the same way they do. I'm just going to start off with this matrix. 0, 1, 3, 4. Minus 1, 2, 0, 3. 2, negative 3, 4, 1. Okay. Now, I want you to tell me what elementary row operation you would do first to try to get to do Gauss elimination on this. What do we really want the first non-zero entry of the first row to be? We want it to be a 1. It's a 0. There's no way you can change that 0 to a 1. So what might you try to do instead? So, yeah, swap them, okay? Ooh, that hurt. So I'm going to do this in gory detail. Row 1 is going to interchange with row 2. That's going to be my first elementary row operation. So that will become -1, 2, 0, 3, 0, 1, 3, 4, and 2, -3, 4, 1. Okay. Now, two things here. They mentioned one, I'm going to mention another. One, they said, these elementary row operations are really simple, but there's lots of little math to do. Okay? They're simple, but they're tedious, is how I put it. Okay? Now, the other thing that's tedious about it, you're having to write numbers over and over and over and over and over again, which to me gets to be very tedious. Like that third row, we can't just leave it off. We can't change anything in it, so you just have to write it down again. So you're writing a lot of the same, and basically all the numbers we wrote the same, we just changed the order. Okay? Now, what's the next thing you would do? Elementary row operation. What? You still don't have a 1 where you want it, do you? Multiply row 1 by -1. So minus row 1 becomes the new row 1. Okay? So here's how I'm going to do it, because I'm plumb lazy. Plus, minus, minus. Okay? That's how I'm going to do it. I should have actually written that out, but I'm not. Okay? It's so much easier to do it that way. Okay? Now we got the 1 where we want it to be. And what do we want next? Yeah, we want a 0 below it. We already got it. So move on to the next one. Multiply the top row by -2. So -2 row 1, add it to row 3. Okay? So the next will be, and here again, you're just copying the first 2 rows. 1, -2, 0, -3. Second row just like it is. 0, 1, 3, and was that a 4? I can't read my writing. Yeah. Okay? What's the new third row? 0. 1. Yep. 4. 7. Perfect. Okay. Now, what we wanted was a 1 here and 0 below it. We got it. What's the next thing we want? A 1 here. And we already got it, so we don't have to do anything to it. And what do we want after that? 0 below it. How will we make that become a 0? So, negative row 2 plus row 3. Perfect. Okay? And that, again, tedious, just writing down the first row. 1, -2, 0, -3. Writing down the second one, because that's the one we're using. 0, 1, 3, 4. Now, what's our new row 3? 0, 0.
No, 1.
1. Three. Perfect. Okay. Now, notice what we got. If this was an augmented matrix representing a system of equations, the first 3 columns represent your variables, the coefficients of the variable, and the last one your constants. If that were the case, now your row reduced coefficient matrix, if that's what it really was, is that diagonal. It's a square matrix, 3 by 3, this part here, and the diagonal elements are 1. Okay? That's exactly what we want for Gauss elimination. What does this tell you? If that was x, y, and z, and those are your constants, then this tells you x, y, and z. Z is equal to 3. 1z is equal to 3. If those represented equations, and that was x2 plus 3x3, or go back to x and y. Y plus 3z equal 4, x plus 2y is equal to 3, and 2x minus 3y plus 4z is equal to 1. If that's where you get started, and that was the coefficient matrix and the augmented matrix, then when you get to this stage, you're in Gaussian form. This would be z is equal to 3, y plus 3z, well that would be 9, y plus 9 is equal to 4, so y must be negative 5, and this would be x minus 2y, which would be plus 10, is equal to minus 3, so x must be minus 13, okay, or whatever, okay? That would then tell you, once you have this diagonal of 1, you can do your back substitution really easily. That's the same thing we did before. That's called Gaussian elimination for matrices. Now, this doesn't have to stand for a system of equations. It can stand for other things, but that's what you would have, okay? Now, did I do it right? Is this looking like the same thing? Oh, they just did the first step on that. And that was exactly, the first step was what we had, minus 1, 2, 0, 3, and then the rest of those were just like they were, okay? And the notation is the row 1 is exchanged for row 2. Oh, and here it is, that's the double arrow, okay? They just do a single arrow with 2 points on it. I do a double arrow with 2 points on it. It doesn't matter. Okay. Now, let's do their B one. I did more than they did in the book. Okay. Let's do the B one. This isn't the same equation. 2, negative 4. 6, negative 2. 1, 3, negative 3, 0, 5, negative 2, 1, 2. Now, what would be your inclination of what to do of an elementary row operation? I can think of 2 things to do that would both be pretty equivalent, though I think one is a better choice. Okay, certainly that's a good choice. Flip the 2 rows to get the one where you wanted it. Can anyone think of the other thing I was thinking of? That's sort of an abstract way of going about it. What is your goal? Yes, divide the top row by 2, or multiply the top row by 1/2. And that's what I'm going to choose to do. And here's how I represent R1 divided by 2. Now, you don't have to do that, but that's what, frankly, I would do. So what would the new row 1 be? 1, negative 2, 3, negative 1. Then write down the others. So again, tedious, tedious, tedious. 3 minus 3, 0. I hope I wrote that right. Yes, I did. Okay. And the next one's 5 minus 2, 1, 2. These are the things that just get a little. Now, I'm not going to carry it forward, but what would you do next? Okay, I would use the top. Always use that 1, that leading 1, minus row 1 plus row 2. You'll get the same thing do it the other way, but except maybe a sign change. But I would I think I would go that way. So that would then be minus this plus this. So that would give you a 0. This would give you a 5. This would give you a minus 6. And that would give you a 1. Right? Minus the top plus the second. And then the next I would do is minus 5 plus this one. Minus 5 row 1 plus row 3. That would give you a 0. That would give you an 8. This would give you a minus 14. And that would give you 7. Okay. But anyway, you just keep going that way. They didn't design these to do more than one step. I'm just telling you that's what I would do. Okay? And that's what they did too. They did 1/2 times row 1 becomes the new row 1. And they do put that next step in there, becomes the new row 1. I kind of leave those out. I'll put it where I want it to be, and that's where it is, just to keep from writing as much. Okay. Now let's go to, this will be a completely different one down here. Original matrix. 1, 2, negative 4, 3. 0, 3, minus 2, minus 1. 2, 1, 5, negative 2. I hope you don't hear my stomach growl. I'm so hungry now I could eat this book almost, but I don't know why. I'm just starving. But I'll try not to let that bother me. What would be your, okay, what do you want this to look like? First thing you want? A 1 there. You got it. So what's the next thing you'd want? 0 below it. You got it. And what's the next thing you'd want? 0 below that. You don't have it, so what would be your elementary row operation? Negative 2, row 1, plus row 3. And I'm going to write it down there, and that means that's where it goes. They do becomes the new row 3. But it's just extra writing, and it gets so crowded, I just tend to leave it like that. Okay, so here again, you just copy the first 2 rows. That's because the leading 1 is what you're using. You don't mess with that. And second, because you got the 0 where you wanted it, you don't mess with that. So again, a lot of tedious writing. Now you get what? 0. 1 more time. It's what? Negative 3. All right, bingo, you got it. Okay. Next. Okay, be careful. Okay, that's the thing. Lots of simple math, but you got to do them together. So many places to make potential errors. So take your time and do it. 13. All right.
Negative 2 and 3 give you 6. Negative 6. Negative 6 and negative 2 give you negative 8.
Negative 8. All right. All right. Going back to multiplying and adding. That's all you're doing, basically. Every now and then a division, but yeah, it's pretty simple. And they got, yeah, same thing we did. Good for them. Now, here is where I tend to cheat a little bit. Okay? And it's not cheating, it's all legal in most states anyway. If I were going to do next, according to the rules, I want to make that a what? So then I'd have to divide by 3. That gives me fractions here. Even if I flip these two, you're still going to have fractions. So before I did that, I would add these 2 rows to give a new row 3, because that's going to give it a 0 down here. And then you get all integers down here, and then go back and divide by 3. Because this, just doing it as it is, adding those gives me a 0 here, 0 down here, a 11 here, and a minus 9 there. So that'll be my new 0, 0, but let's say 11 minus 9. Then go back and change this to 0, 1, negative 2/3, negative 1/3. Why mess with fractions any more than you have to? You got to mess with them, but why don't introduce them any sooner than you have to? So I would do that, even though that's technically not the order you do them, but it just makes life easier. And I'm all for an easy life, okay? Yes, okay. Just kidding, kind of. Okay. So, let's start from scratch and do a whole problem here. Okay. Oh, man. Here is your linear system of equations. X minus 2y plus 3z is equal to 9. Minus x plus 3y is equal to negative 4. 2x minus 5y plus 5z is equal to 17. Now, it seems like to me, I've seen this one before, but I can't swear to it, but I think we have. Okay? And probably going to see it again or something awfully close to it. Now, if we were going to change this to a matrix, what would that matrix be? By the way, matrices are usually put inside brackets. Okay? So what would that matrix be? One. Negative 2. 3. 9. Perfect. Next. Negative 1. 3. 0. Negative 4. Next. 2. 17. Perfect. Now, at least to begin with, it's not a bad idea to remind yourself what things are. These are X's, these are Y's, and these are Z's. Just label your columns like that. I don't usually, but it's okay to do if you tend to forget. Okay? And these are just numbers, so don't put anything over them. Like I said, in the old day, I put a dotted line there just to remind myself those are the constants. But you don't have to. What's the first thing we want to happen in that matrix? A 1, and we already got it. Nice. So what's the next thing we want to happen?
0.
The one below that, the negative 1 below that be a 0. How do we make that happen? Yeah, just row 1 plus row 2. That will do it. And that becomes the new row 2. That's why I wrote it down there. So that means we write over our row 1. 1, negative 2, 3, 9. Okay? What's our new row 2? 0, 1, 3, 5. All right, what's the next thing we want to happen? The 2 becomes a 0. How do we make that happen? Negative 2 row 1 plus row 3. And that will do it. So what does that give us? 0. And negative 1. Negative 1. What's that?
Negative 16. No. Negative 18. 17 is 2. No, negative 2. Right? Yeah. No, negative 1.
Yeah, all right. Whew, he argues with himself a lot, doesn't he? Okay.
I do.
All right.
That's why I'm slow in math. I always double check myself.
Yeah, always do. It's a good idea.
That's why I know these days.
That's why it's a good thing to write the operations over here so you do it. Okay. Now, in case you didn't pick up, the reason I write it here, this is just, these two had to be 0, had to be 1, 3, 5. Okay, that's what goes there. This one is minus 2 times the top plus the third. So Minus 2 times 1 is minus 2 plus 2 is 0. Minus 2 times minus 2 is plus 4, minus 5 is minus 1. Minus 2 times this is minus 6 plus 5 is minus 1. Minus 18 plus 17 is minus 1. So let your fingers do the walking, you know, and that sometimes, huh?
My eyes was doing the walk.
Yeah, and they were getting caught across sometime too, weren't they? Okay, no, yeah. Be careful. Take whatever it is. Okay, what you want to happen next?
I draw 2 to the
Okay, what you want to happen next is the first non-zero. See, you dealt with this non-zero entry being 1 and eliminate everything below it. Then you go to the second row. Want the first non-zero element to be a 1. You got it already. Don't have to do anything. Then you want zeros below it, and then you see, just add the 2 rows together. So row 2 plus row 3. That's all you do. Row 2 plus row 3. Which means we write down row 1 again. 1, negative 2, 3, 9. Row 2 we're using, so we write it down. 0, 1, 3, 5. And then add the 2 together, and what do you get? 0, 0, 2, 4. Okay. Now what's this?
If this one was a square metric, this time we have a 1, 1, 2 instead of 1, 1, 1.
Okay. So guess what? I was just going to ask that.
Divide the last row by 2.
Right? Because of this. Remember how we did it. First thing we want, 1 here, 0's below it. Then we want a 1 here, 0's below it. Then we want a 1 there, and how do you get that to be a 1? Divide by 2. Or multiply by 1/2, either one you want to do. The book does 1/2 row 3. I do row 3 over 2. It says the same thing. And this becomes, and you have to write all those down again, 1, negative 2, 3, 9, and this would be a 0, 1, 3, 5, and this becomes what? 0, 0, what? 1, 2. Now you might, if you need the refresher, go back and write, these are the coefficients for x, these are coefficients for y, these are coefficients for z. What does this tell us? Z equal to? Y plus what? Huh?
Give me a second.
Okay. Seconds up. Okay.
Then add another one. It's 5 minus 4 is 1.
Okay.
We subtracting, right?
Okay.
We add 1 plus 3 minus 5, right?
Okay.
That's how we
Okay, it's y plus 3. No. Y plus 3 times z. See, this is your y. 1y plus 3z equal 5. Y plus 3 times 2 equal 5. Okay. Remember what these stand for. These are coefficients for x, coefficients for y, coefficients for z. These are equal signs here, these are numbers on the other side. So this would be 1y plus 3z equal 5. So this is 1y plus z is 2, so 3 times 2 equal 5, and this will be y is equal to negative 1. All right, y is equal to negative 1. And the top one would be? What's that?
That one would be give me a calculator.
It's not that bad. It's x, the 1 is the coefficient of x, minus 2 times minus 1, which would be plus 2, plus 3 times 2 is plus 6, is equal to 9. X equal 1. Perfect. It's not that bad.
It's not that bad, but I needed my calculator.
Okay.
On my lunch.
I think writing it down is going to help. So what's our one and only one solution? 1, negative 1, 2. Okay? Let's see if that works.
We're holding the class up.
What's that?
We're holding the class. I don't know, somebody needed to.
Someone walked in?
Yeah, because it's bedtime.
Is it time?
Are we on time?
How could it be we just were going good? No, we're not out of time, are we?
We are.
Yeah, we get out at 12:45.
Yeah. Oh, yeah, you're right. Yeah. How could it be? Okay.
Come on in.
All right. But hey, but real quickly, let's check and see, because we like to make sure we're right? 1 plus 4, right? Plus 2. 1 plus 2 is 3, plus 6 is 9. That works. Minus 1, minus 3,
That's negative 4.
minus 4, that right. And then 2 plus 5 is 7.
17, that's right.
Plus 10, 17. Perfect. Okay.
If we're late, what time is it right now?
It is a little after 12:45. Okay. So, let me give you homework exercises. I know you don't want to leave home without those. We'll start next time with row echelon form, bottom of the page. Okay, let me erase this so I'll know which mark I'm dealing with. Okay, put this in place. And what we have here, homework exercise, this is a long section. Okay, do any of the odds 1 through 5? Do either 7 or 9 or both. They're all at Calc Chat, by the way. Do any of the odds 11 through 17? We haven't done row echelon form, so skip that and go up and do any of the odds 25 through 29. No, through 37. And then we'll come back and wrap the rest of those up next time. All right, good deal.